In this video, I'm going to summarize how the number of ATP that we get from the breakdown of glucose is affected by where that glucose came from and which energy system we use to get the ATP. On this slide, I'm going to summarize the anaerobic breakdown of glucose. And we're going to be focusing here on glucose in its free form. When we're talking about free glucose, we're just talking about glucose that came into the muscle from the blood. And so you should also note here that anaerobic breakdown just means a type of breakdown that doesn't require oxygen. So for the anaerobic breakdown of free glucose, we start with free glucose, and we have to pay 2 molecules of ATP to get the process started. So these two things are what we consider our substrates. Our substrates go into our glycolysis box, and a bunch of stuff happens. You don't need to worry about what exactly that stuff is. But at the end of glycolysis, you end up gaining 2 molecules of pyruvate, 2 molecules of NADH, and 2 molecules of ATP. You'll see that I have a number 4 in front of ATP, and that number 4 is crossed out. The reason that I did that is because technically the process of glycolysis makes 4 molecules of ATP, so your total ATP count is 4, but you had to pay 2 molecules of ATP in order to get this process started, so you really only gained 2 completely new molecules of ATP. You'll also see on the slide that I mentioned what the rate-limiting enzyme is and what inhibits and stimulates that rate-limiting enzyme. You should know that for the exam, but that's kind of beyond the purpose of what I want to do with this set of slides. So moving on to our next example. In this example, we're talking about the anaerobic breakdown still, but this time we're using glucose that came from glycogen. So when you use glucose that came from glycogen, or from the storage form of carbohydrate in the muscle, you only need to use 1 molecule of ATP in order to get glycolysis started. So here our substrates are glucose and 1 ATP, and at the end of glycolysis, you end up with 2 molecules of pyruvate, 2 molecules of NADH, and a gain of 3 ATP. Again, glycolysis makes 4 ATP, but you had to pay 1 molecule of ATP in order to get the process started, so our gain is 3 ATP. So that's kind of the gist of the anaerobic breakdown. The big difference between the anaerobic breakdown of free glucose versus glucose from glycogen is if you're starting with free glucose, you pay 2 molecules of ATP, which means that you have a gain of 2 ATP. If you're using glucose from glycogen, you pay 1 molecule of ATP, which means you have a gain of 3 ATP. On the next 2 slides, I'm going to summarize what's called the complete aerobic breakdown of glucose. So this is where we start with glucose and we get as much ATP out of the process as we possibly can. So for the complete aerobic breakdown, we have to use what was left over from glycolysis, and kind of the leftover parts of glycolysis end up going into the aerobic system. So if we started with free glucose, at the end of glycolysis we got 2 pyruvates, 2 NADHs, and a gain of 2 ATP. Those pyruvate molecules then went into the first stage of the aerobic system, the production of acetyl-CoA. At the end of the production of acetyl-CoA, those 2 pyruvate molecules were converted to 2 acetyl-CoA and 2 NADHs. You get 1 acetyl-CoA and 1 NADH for each pyruvate, and so since you put 2 in, you get 2 of each item out. The acetyl-CoA from this stage then goes into the Krebs cycle. At the end of the Krebs cycle, we get 3 NADH, 1 FADH2, and 1 GTP or ATP for each acetyl-CoA. So since 2 acetyl-CoA went into Krebs, we end up with a total gain of 6 NADH, 2 FADH2, and 2 ATP. Now we're going to move on to the electron transport chain. The electron transport chain is really neat because it can pull in all the energy carriers from earlier stages in the breakdown process. So the NADHs that were left over from glycolysis, they go to the electron transport chain. The NADHs left over from the production of acetyl-CoA also go to the electron transport chain, and the NADHs and FADH2s from the Krebs cycle will go to the electron transport chain. Every time an NADH molecule interacts with the electron transport chain, you get 2.5 molecules of ATP. So if you count up all the NADHs that are on this slide, you'll get 10. So 10 times 2.5 gives you 25 ATPs that we get from all the NADHs we produce. If you count up the number of FADH2s that we see on this slide, you get 2. So those 2 FADHs, when they interact with the electron transport chain, they each are used to produce 1.5 ATP. So 2 times 1.5 gives you 3 ATPs from your FADH2s. So if you add up the 2 ATPs that you got from glycolysis, the 2 ATPs that you got from the Krebs cycle, the 25 ATPs that you got from all your NADHs, and the 3 ATPs that you got from your FADH2s, you get a total of 32 ATP. So if I were to ask how many ATP do you get from the complete aerobic breakdown of free glucose, your answer should be 32 ATP. On this next slide, we're summarizing the complete aerobic breakdown of glucose from glycogen. So again, we're going to say that glycolysis happened and we were left with 2 pyruvates, 2 NADHs, and a gain of 3 ATP. For aerobic breakdown, those pyruvate molecules then go into the production of acetyl-CoA stage. The 2 pyruvates are used to make 2 acetyl-CoAs and 2 NADHs. Those acetyl-CoA molecules then will go into the Krebs cycle, and in the Krebs cycle you'll get 6 NADHs, 2 FADH2s, and 2 ATPs. And then finally, all of the NADHs and FADH2s will feed into the electron transport chain. Again, if you count up all the NADHs on this slide, you'll see that there are 10 NADHs, which means that those 10 NADHs can give you a total of 25 ATPs. And you'll see that there are 2 FADH2s. Those 2 FADH2s each get converted to 1.5 ATP, so you get a total of 3 ATPs from all your FADH2s. So to summarize this slide, you end up getting 3 ATP from glycolysis, 2 ATP from the Krebs cycle, 25 ATP from all of your NADHs, and 3 ATP from your FADH2. This gives you a total of 33 ATP. So if I were to ask how many ATP do you get from the complete aerobic breakdown of glucose from glycogen, your answer should be 33 ATP.